There we go. I had one page turned. All right, so removable discontinuities come from rational functions. A piecewise function can be used to fill the hole. So we're going to be looking at rational functions here and trying to fill in holes. All right, so remember there's two kinds of discontinuities that a rational function can have. So rational function discontinuities. We can have infinite discontinuities. And these are non-removable. Right? So if we have an infinite discontinuity, we're not doing a darn thing about it. And then we have our holes, right? Holes in the graph. And those are removable discontinuities. So we're looking for holes. We're going to fill in the holes. All right, so let's look at this one. Right, removing a discontinuity. Right, so if we have an infinite discontinuity, we're not really going to care about it. Right, so we're not looking to reduce anything. Right, this isn't taking a limit. We can't really, we're not changing what the graph looks like. Right, we can't change the function. What we're looking for is holes, the removable discontinuities. All right, so here we have a function f of x equals x cubed minus 7x minus 6 divided by x squared minus 9. And you might notice the answer on the other side rewritten. But don't worry about that right now. Let's worry about how do we get to there. All right, so you may look at the numerator and go, oh, that's not so easy to factor. And that really wouldn't be easy to factor, right? We would need to use some synthetic division, right? We'd have to use a rational root test, figure out possible roots, and use some synthetic division, right? But we're not really worried about what those factors are. We're just worried about where the holes are, right? So let's factor the really easy thing, which is the denominator, and not worry so much about the numerator right now. All right, so we have f of x equals x cubed minus 7x minus 6 divided by x minus 3 and x plus 3. All right, so now if there's a hole, it's because either 3 is x cubed minus 7x minus 6, or negative 3 is a factor of x cubed minus 7x minus 6. Okay? So you can plug them in and see what you got as an answer. Right? Do you get 0? Or you can just try the only two possibilities for holes, right? So our only possible holes are going to be from the, it's going to be, we would have the same factor, the numerator and denominator, right? So only possible holes we could have is at x equals 3 or x equals negative 3, poor equal sign there. All right, so let's test out 3 and negative 3 and see who is the hole. I'm going to write this over here because that just didn't look so good. Oops. I have to remember. Well, now look what happened. But at least the equal sign looks better. I'll rewrite the x. Every time I put the pen down, you might notice it on the top of the screen. I hit that arrow up there, and I have to change it to yellow. All right, so let's do a little synthetic division. So by the way, there are steps there in words. I'm not going to read through those. You can read through those if you like. I'm just kind of saying it the way I think, all right? But you can also look over there as well and get both ways. All right, so let's try, see what happens with 3. I plug in 3. I'm going to use synthetic substitution, right? And so remember that I'm missing a square term. So it's going to be 1, 0, negative 7, negative 6. There's no x squared term. You got to represent them. Otherwise, you're combining terms that aren't like. All right, so bring down the 1. 1 times 3 is 3. Add, we get 3. 3 times 3 is 9. Add 2. 6, and that's 0. Oh, look at that. 3 is definitely a factor in the numerator. Right? How about in the in the numerator? How about negative 3? Is that also a factor? Let's find out. All right, so again, 1, 0, negative 7, and negative 6. Bring down the 1, that would give us negative 3. We multiply, add, negative 3. Multiply, we get 9. Add, we get 2. And no, that's not, because we get negative 12. All right, so where we got 0 as a remainder, this one here is a removable discontinuity, and I can't fit the whole word in. So I'm going to write the word whole because it will take me less space. But we're going to call it removable and non-removable, right? Or infinite, not whole, but we'll put whole there for now. Now, what's the negative 3? Well, the negative 3 is actually going to be a vertical asymptote. So you can't remove the vertical asymptote. That's an infinite discontinuity, right? So only this one is removable. Right, so now when we write our function, right, and yes, we have it written there, I'm going to give it a new name, right, because it's no longer f of x. Right, now it's something else because I've changed the function. I filled in the hole. It's not exactly the same function. Right, so, and that's my best bracket. Sorry about that. Right, so we're not going to be canceling things out because that will change our function, our original function. The only thing we're changing, right, is still a rational function. The thing we're changing is we're adding one new piece to fill in the hole. Matter of fact, that piece is literally a point to fill the hole. All right, so this is just going to stay x cubed minus 7x minus 6. Right, and this is going to stay x squared minus 9. But we're not going to use the hole, all right? So when x is not equal to 3. And you might say, hey, but wait, you can't use negative 3. Yeah, you can't use negative 3 because it's not part of the domain, right? But specifically, when I got to say x not equal to 3 because I'm going to plug in a value for 3. And there's no value I could plug in for negative 3 to make that any better. So, well, how do I know what value to plug in? Well, now you go to your reduced function, right? You go to the reduced function and you plug in. All right, so my reduced function, we use synthetic division, right? And we were able to reduce it. Here's the reduced function. That's what's going to give me my value to plug my hole in, right? And I'll do ones without some, I should probably just get rid of the writing. So we're going to use the reduce function to find the value that plugs in the hole. Right? Actually, that's how we find the hole to begin with if we're graphing a rational function. Right? So we know that since 3 is a solution, right, x minus 3 is a factor. So that numerator is x minus 3. Well, what's the rest? Well, that right there. Right? That's the rest. Right? We could factor that. That's going to be x plus 2 times x plus 1. There's really no point in factoring it because it's not canceling out with anything else. So I'm just going to leave it as x squared plus 3x plus 2. It's just really not worth factoring it, even though it wasn't that difficult. Right? And in the bottom, of course, we would have x minus 3 times x plus 3. Now we can cancel that out. Actually, the only reason that you might want to factor that that numerator, is because it is a little easier on the substitution. So actually, I am gonna, because it's really easy. I just said it, right? I just did it in my head, right? Multiplies to give me 2, adds to give me 3 is 2 and 1. So I am going to actually write that as x plus 2, x plus 1 for no other reason than it's easier. The math's a little easier. All right, so now we're plugging in what value? The value we crossed off, right? So x is going to equal 3, and we're going to find out what value are we losing because there's a hole. All right, so we'd have 3 plus 2 times 3 plus 1. And so I want to double check, yep. I hope I get 10/3. Right? And then the other one is, but I don't get 10/3. Do I have a factor in here? X plus 2, x plus 1. Really don't see anything. All right, you know what? Because that's 5 times, oh wait, never mind. It's going to reduce. Oh, silly me. I just had to think for a moment. If I would have just written this, 3 plus 3, I'm wondering, does it match 10 and 3? Well, it will when we reduce. All right. All right, where's the rest of my words? All right, so this is 5 times 4, that's 20. Hello, words. Just stopped writing. All right, and in the denominator, we have 3 plus 3, and that's 6. All right, come on. I don't want to rewrite everything. I don't want to retape everything. We should be done now. I've never had it just stop like this. Literally just stop. Here, let's just erase it and write it again. All right. Oops, that was a 3. So we'll plug in the 3. So I was just checking to make sure, I should get 10/3, and forgot that I would have 3 plus 3, which is going to be 6. All right, so that's going to be 26, which of course is 10/3. All right, so now we just fill in our hole by saying what the value is going to be, and it's actually what we have above there, what the value is going to be when x is 3. And of course, that's just going to be 10/3 when x is 3. And that's all the steps there is, right? Right, so in a whole lot of words, probably more words than were needed, there are steps at the bottom, but I have the steps right up there, right? So don't worry if one of them is a little harder to factor than the other. Factor the easier one, right? And that will give you the only possible places there could be a hole. And once you know where there could be a hole, just test them. Use synthetic substitution test. See which one gives you a remainder 0. Right? That one's the factor. Right? And then you can use that to rewrite it. Here it just happened to be so easy to just factor the thing, and then we can just plug in. You plug into the reduced function. Right? If you plugged into the other one, you just get 0 of 0. And that will tell you where your hole is, right? Because that's the value you can't use. That's all there is to this. So I have one more example here. To remove the discontinuity, so here we have a discontinuity at 1, right? If I plug 1 in the denominator, whoo, that's a problem. And so is -1, right? So, but the one at 1 is removable, and the one at -1 is not removable. All right, so here we have it factored. Remember the pattern of factoring, the difference of cubes. Right? So difference of cubes, the first one's going to be cube root minus cube root. And then you're going to have the cube root squared. Right? So the cube root of x cubed is x, and x squared as well, x squared. All right? And then you're going to, and then at the last term is going to be the cube root. So it's a little reminder here on how to factor this. So this one here is always the cube root, so let's call that one a and b. All right, so this is always the cube root of a, and then minus the cube root of b. And then this one is going to be the cube root of a squared, and this is going to be the cube root of a times the cube root of b, that's the middle term, and then the last one is the cube root of b squared. That's a helpful thing to remember, right, on the factoring there. All right, so here when we factor, we see, oh, an x minus 1. So that one is in both. This one is a removable. Let's move this whole thing down. Actually, I'm just going to go to the screen. There it goes. All right, so this one here is removable. That's the whole. And this one here is infinite. And infinite is not removable, right? So we're not doing anything about that one. Right? So we know we have a hole at 1. So we have to figure out where the hole is, what the value of the, what the value, we know where it's 1. What the value of the function is when x is 1, once we take that problem factor out. Right? If we don't take the problem factor out, you just get 0 over 0. Right? So you plug into the reduced function, and that gave us 3/2. Right? And so that's where the hole is. And now when you rewrite it as a piecewise function, you just fill in the hole. Right? So f of x equals, we have the same function, x cubed minus 1 divided by x squared minus 1, and not except when x is not 1. Right? So that's the function to use except when x is 1. Right? We have to do that, otherwise we're no longer a function. This is a piecewise function. I can't have two values for x. Right? So I've got to take -1 out. Even though it's not part of the domain, even though I couldn't possibly plug in 1 there, I've got to take 1 out. Right? And because we're plugging in that hole, 3/2 when x is 1. Right? So the other discontinuity is at -1. It cannot be removed. It's infinite. So I'm going to stop here, and I have some problems for you to do. Do your best to figure out, you're looking for where the removable discontinuities are, and let's see how you do with those, and then I'll go over them. So just do your best, and so bye for now.